This paper introduces the notion of collision cones for quadric surfaces in n dimensions. The problem of path planning in n-dimensional spaces has attracted much interest, and in general such n-dimensional spaces may contain both stationary and moving obstacles, and many sampling-based planners such as the PRMs and RRTs explore regions of this n-dimensional space and look for potential collisions with obstacles. It would be immensely helpful if we could characterize collision-free regions within the space, and if so characterized, the sampling-based planners then need to explore only those regions. In this paper, we are performing the characterization of the collision-free regions by using the notion of collision cones. And a collision cone is essentially the set of heading directions that would cause an object A to be on a collision course with a moving object B. In this figure, A represents a point object having to navigate through an n-dimensional configuration space with multiple moving obstacles B1, B2, B3 and so on, moving with velocities VB1, VB2, VB3, etc. The collision cones from A to each of these obstacles are represented as C1, C2, C3, etc. In cluttered environments where the objects are moving in close proximity, the shapes of the objects play an important role in the determination of collision avoidance maneuvers. In this paper, we are providing an analytical characterization of the collision cones associated with a class of hyperquadric surfaces, which can serve as efficient bounding volumes for a large class of objects. And with knowledge of these cones, the sampling planner can then evaluate waypoint samples that lie outside these cones. The n-dimensional cones can also comprise of cones of desirable heading angles. So for instance, in RRT methods, it has been shown that for problems that seek to minimize path length, the subset of states that can improve a solution can be described by a prolate hyperspheroid. And in such problems, the hyperspheroid essentially is a region within which the trajectories need to lie, since the optimal path is contained inside the hyperspheroid. And the cones that we would determine here would basically be the cone of desirable heading angles, and then the sampling-based planner needs to sample only the waypoints that lie within this cone. This is a picture of a four-dimensional collision cone. The three coordinate axes are basically the set of heading angles that would lead an object A to collide with a hyperspheroid which is moving in four-dimensional space.